Okay, so we want to find the shell method to calculate the volume of our blue region here, rotated about the y-axis. I'm just going to sort of talk through this process the way I'm used to thinking about it, and hopefully you'll find this helpful. Okay, so first up, for the shell method, I want to draw myself a typical rectangle inside that region. And for the shell method, that region is parallel. That's not the color I wanted. That region is parallel to the axis of rotation, in this case, the y-axis. And I need that to help me figure out how to set up my integral. I'm going to go ahead and, just for aesthetic reasons, color in this shape. But that blue, kind of not quite a triangle shape, that's going to be rotated around, and we're going to get, a somewhat conical shape. Okay. So what I do is I imagine this white triangle being spun around, and I'm going to follow the path. Oh, why is that blue? Oh, because I just colored in the blue thing. Haha. I'm going to follow, in my imagination, the path of that white typical rectangle. And as we spin it around the y-axis, the top of it is going to begin to look like this. I just realized my typo over there, but we're just gonna go with it. Okay, so this is the shape that white rectangle creates. And so what I'm gonna do is I am going to, with magical scissors, cut this open. Actually, yeah. We're going to cut that open, and I am going to unroll it. When it's unrolled and flattened out, it's very much like the label off a can of soup or SpaghettiOs or whatever your favorite thing was. And we are going to find the volume of just that very, 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 very thin box. Okay, and the volume would be the dimensions. So I'm going to start with the easiest thing. This dimension right here. Oh, no, let me get a pointer. This dimension right here, this is going to be equivalent to the thickness of this typical rectangle. And so what I'm looking at here is, what is the thickness here? I know this is a super, super small, so this is either a small change in X or a small change in Y. And so I can see that there's just a small change here in the X-axis. So I am going to use the differential dx to represent that thickness there and there. So next up is, what is the height of this thing? Well, right here, I'm already being told that I'm going to be integrating with respect to X. So I want the height of this thing to be represented as some kind of function of X. Okay, so where does this height come from? Well, it's this height right here. So we have to imagine, as I move this rectangle throughout the region, that the height is going to be different depending on which x's I'm sitting in between, so to speak. Okay? So, sorry, just I had a brain freeze. One way that we can talk about the height of this rectangle is we can imagine it's going to be this y value minus this y value. That's going to be the height of it here. If I were to do a similar triangle right here, you know what? I can draw it in and then undo it. I love this. If I were to find the height of that rectangle, it would still be this y value minus this y value. That would be its distance, okay? And that's all I need for right here. I just need that distance, but I want it to be a function of x. We're gonna set that aside for a moment, okay? So this y value is consistently 27. This y value, let me rewind. I wanna make sure that's 100% clear. Anywhere I draw a typical rectangle, it's going to have a top y value of 27, a top y value of 27, a top y value of 27. The bottom is going to have a different y value from here to here to here, and that's where we're going to use this function of x. But I don't want to spoil the surprise too much. Ugh, I'm trying to undo. Oh gosh. It's undoing me pointing. There we go. That was silly. Okay, so I'm going to make a note down here. This thickness is the y value 27 on top minus the y value on bottom. But what determines the y value? The y value is going to be equivalent to whatever x to the 2/3 power is. All right, so then the last dimension that we have left to determine is this distance right here. But to find this, we need to recall that this came from a circular cylinder beforehand. Let me do a quick redraw because I just remembered I do want to point out something. So, okay. So this distance is going to be the equivalent to the circumference. Yeah, sorry. My brain was like, circumference or diameter? Sorry, and that's the drugs at work. Okay, so this distance is the unrolled version of this circular cylinder. So this distance from here back to here is going to be equivalent to, the circumference. So how do we find the circumference? The circumference is going to equal 2 pi times the radius. And I'm going to make a space here for the radius. I should have used a different color, but so be it. Okay, so what is the radius of this circle? And we can use either this circle or this circle because this distance, dx, is negligible. It's essentially 0. Okay, so to find this radius, we need to know where the center is. The center, of course, is right here, but where was the center from the rolled up side? This is our center, okay? So this distance right here from the y-axis to our typical rectangle, that's going to be equivalent to the radius. That's the same distance from here to here. Here's my typical rectangle. I keep pausing on the word rectangle because my first instinct is to say triangle, and I know that's wrong. So that's why that sounds weird as I say it. Okay, typical rectangle. This distance is the radius. So how do we find that distance? Well, notice that distance is going to be equivalent to whatever the x value is, wherever the typical rectangle starts, okay? So since from here, I don't know how to make this picture, to here, no, that's backwards, that's stupid, undo. Anyway, that's going to equal whatever our value x is at that point. And more to the point, right here, the circumference is going to be 2 pi times the radius. The radius is equivalent to whatever the x value is, which is nice because recall we already wanted to set up our differentiation by x. Okay, let's set up this volume by multiplying these three things together, so to speak. So I have 2 pi times x times the height of that, 27 minus x to the 2/3. And I apologize if my hand was covering up the microphone. I've been trying to avoid that. I know how to fix this. There we go. I flipped my iPad upside down. Okay, so that is the height. And then the thickness, that's my dx. So that's the volume of one of these little cans, one of these little cylinders. But to find the total volume, we need to add up the accumulation of all of these little typical rectangles generated throughout the region. So that's where the integration comes in. It is the summation of all of those. And we are integrating with respect to x. So we need some limits of integration. So I'm just going to get this ready. X here to x there. You probably don't put the x's there, and that's okay, and that's fine if you don't. In fact, the overwhelming majority of people don't. So from which x do I start until which x do I finish? So imagine, again, this white rectangle sliding throughout the region. When is x the smallest? Right here at x equals 0. So that's going to be my lower limit. And then we're going to slide that rectangle through until we get to here. This is going to be the farthest right that a typical rectangle might fit. So we need to do a little calculation right here. What is this particular x value? So to answer that, we've got to figure out x to the what power, what number raised to the 2/3 power? That's the real question. I knew I was fumbling it. Okay, so what does this x equal? It's whatever number we need to raise to the 2/3 power to get the y value 27. So let me do a little erasing. Make some room for some scratch work. So x to the what power equals 2/3. No, what number raised to the 2/3 power equals 27? This can get overly complicated, but let me try to make this as simple as I can. One way that I can think about this is I can take this number, raise it to the 3rd power, and that's going to leave me with x squared equals that number, and I'm going to be honest, I do know what it is. No, I don't. Yes, I do. It's 729. No, it's not. That's what 27 squared is, not 27 to the 3rd power. My first instinct was right. I don't know what that number is. Hang on, let me pull up my calculator. Okay, checked my calculator, and 27 to the third power is this 19,683. And I'm going to say I'm a little surprised. I was expecting our value of x to come out to be quite a bit nicer. But now I think I know what to anticipate. Anyway, so if that's true, then we're going to be lazy and just say x equals the square root of 19,683. We're not going to try and simplify that, even though we absolutely could. Anyway, I'm just going to leave that. But that is my upper limit. No, you know what? I'm gonna change it even more. I'm gonna get rid of this 19,000 number. And we're just gonna call, oh no, that's not what I wanna do. Fun and games. Eraser time. Nope, that's not an eraser. All right, what do we, oh, and I went, there we go. Erasing. Right here, let's go all the way back to this. Instead of just doing this in one step, in multiple steps, I'm just gonna do this in one step. I'm gonna wave my hand at something, so don't show this to any other real math people. So we're gonna take this and raise both sides to the 3/2 power. In essence, what happens right here is when I multiply these exponents together and I get 1. There is one thing that I have to be conscientious about, and that is at this moment right here, I am taking the square root to undo squaring. And so that means I need to be conscientious of the two possible solutions. The two solutions are moot because of our region right here. It's possible that x could be the positive or the negative. There's two fun and games. Angel, you took me. You know, this was when we talked about the square root property, and you had to consider both the positive and the negative square root when you used a square root to undo squaring. For example, I'm thinking of a number. When I square that number, I get 16. I could be thinking of the number 4, or I could be thinking of the negative 4. I'm taking way too long. I thought I was trying to get past this earlier. I don't have to consider plus or minus in this case because my region is bound between x equals 0 and x equals whatever this number is. I know over here this is going to be positively valued. That's all I really, really wanted to get at. And so when this simplifies over here, I get x equals, and I only have to worry about writing 27 to the positive 27 to the 3/2 power. And so that is going to be my upper limit of integration. (27 to the 3/2 to the 5). What's wrong? It wasn't writing up there, jerk. Okay. So that is us setting up the integral. Okay, I'm going to clear that out. And I'm going to go ahead and clear this out. This out too. And we'll just see how much room I need to work this integral. What I'm going to do to save you the minutes is I'm going to pause my recording in between my own little steps. And you can likewise pause food's here when you need time to kind of process. I don't know. We'll see how it goes. But let's see. What am I going to do? First thing that I'm going to do to clean up this integral is I'm going to distribute this x inside parentheses, and I'm going to go ahead and move that 2 pi out. He's not bothering me, but we're not going to need him for the integration, I don't believe. So I'm going to pause just to write it down, and then I'll talk about what I'm going to do next. Okay, so once I pull out that 2 pi and distribute that x, I end up with 27x minus x to the 5/3. As I was writing this, I realized this may not be obvious, but when I multiplied this x by this x, they have the same base, so I can add their exponents together. This has an exponent of 1. 1 plus 2/3 is equivalent to 3/3 plus 2/3, and so that's where I got the 5/3 from. Okay, so what happens next? I have not quite a polynomial, but I can just use I don't know the technical names of all of these integration properties, but I can basically consider each term and integrate them independently. And so I'm just going to use power rule on this, power rule on this, and we'll see what happens after that. You know what? Let me talk through power rule right now before I write it down. I know that when I'm integrating, I'm like finding antiderivatives, and so I'm going to have to increase this exponent by 1 and then do some stuff here with the coefficients. So this is going to go up to 2. And here, when I go up by 1, I'm going to add another 3/3 to this. And so I'm going to get up 8/3, and I'm going to have to do some stuff with the coefficient there as well. All right, let me write it down. Okay, so as promised, I got an x squared here, but remembering that if I were to redifferentiate using power rule, I would want to get 27x back. So I need a 1/2 here to counter that multiplying by 2. Likewise, I would need to multiply to differentiate. I would need to multiply by an 8/3, but I want my coefficient to be 1, so I have at the ready its reciprocal 3/8, and then I would subtract 1 from that to get that 5/3. Okay. So next up, we plug in our limits of integration, and I'll write that down here, but I want to go ahead and acknowledge, so I don't have to write it down, that when I do the second half and I plug in the lower limits of integration, 0 squared is 0, 0 times anything is 0, so this all becomes 0, and very, very similarly, 0 to the 8/3 power is also 0, so this is all going to zero out. So when x equals 0, this all gets zeroed out. So I'm only going to need to worry about plugging in this 27 to the 3/2 power. Okay, so I've plugged in our 27 to the 3/2 power for this x here. 27 to the 3/2 power plugged in for that x that's being squared, coefficient of 27/2. And then when I plug 27 to the 3/2 power here, I get it here, raised to the 8/3, multiplied by the coefficient 3/8. Okay, next up, we're going to have some cleanup. This was the benefit of leaving our upper limit of integration as 27 to the 3/2. The cleanup with exponents is going to go much nicer. So what's going to happen is, yes, right here, when I multiply 3/2 by 2, the 2's cancel, and this is going to be left with just a 27 to the 3rd power, which was that 19,000 number that we saw earlier that I've already forgotten, minus, right here, when I multiply this exponent 3/2 by this exponent 8/3, the 3's are going to cancel each other out. 8 divided by 2 is going to equal 4. So this all reduces down to 4. So this is equaling 27 to the 4th power. Okay? I'm going to come back with those numbers. Okay, I'm not trusting my judgment, so I'm going to think out loud instead of predetermining what I'm going to say here, Angel. Truth be told, we're just at like the simplifying stage, and I don't know what the easiest way to go about this would be for everyone involved. So like, for example, I'm seeing that we're multiplying a 27 to the 3rd power times another 27, which is going to give me a 27 to the 4th power, which is nice because here I have a 27 to the 4th power, and in some ways we can think of just adding or subtracting so many 27s to the fourth. And I do like that, and I think that's going to be the good way to go. But I'm also anticipating some stuff and thinking, should we get common denominators here and here, or should I distribute this 2 and simplify, but then we'll still need common denominators here and here. Why don't I do those? Why don't I try to not do too many steps at once? Yes. So here are the 2 things that I'm going to do. I'm going to combine these 27s and call this 27 to the fourth. And I'm going to, and I'm going to distribute the 2 inside to simplify this to 1 and to simplify this to 4. So this will become 3/4. Okay, so I did as I promised, and this is looking so gorgeous. So then the next thing that I'm going to do is I'm just going to mentally do a little fraction math. If I have 1/27 to the fourth there, that's equal to 4/4 of 27 to the fourth. So when I subtract 3/4 from 4/4, I'm going to have 1/4 of 27 to the fourth power. And I'm going to clean that up, and we're going to be so damn close. So then the last thing that we got to do is finally bust that calculator back out and figure out what 27 to the fourth power is. We'll multiply that by pi up top. We'll divide by 4 on bottom. I know because 27 isn't divisible by 4. No other power of 27 is also going to be divisible by 4, so I am confident that the denominator is going to be 4. Okay, I'll see you on the other side of a calculator. Okay, according to my calculator, 27 to the fourth power is 531,441 multiplied by that pi out front divided by 4. That should hopefully be the correct answer.